Okay, so now let's talk about the intensity of light once it has passed through a polarizing sheet or more than one polarizing sheet. Let's start off with when we have light that is unpolarized. So it's coming in, the way we would draw that is by doing our cross vectors, remember, and it's coming in towards a polarizing sheet. So for example, if we have a polarizing sheet that is parallel to the y direction, or it's parallel to the vertical direction, only electromagnetic waves with electric fields that have a vertical component are going to pass through the sheet. And another way of saying that is that all of the horizontal components, or the Z components of the electric fields, are going to be absorbed by the sheet. Now remember, for unpolarized light, all the light waves are coming in and the electric fields are randomly orientated. What this means is if we were to sort of average out the direction of these electric field vectors, we're going to find basically an even number on the right hand side, or even number on the positive Z, even number on the negative Z, even on the positive Y, and even on the negative Y. So what this basically means is that if all the Z components are absorbed, half of the intensity is going to be absorbed by the polarizing sheet. Because remember, we've kind of got even amounts or even numbers of the electric field, even amounts of the electric field vectors are orientated around this thing. If we can assume what we call a uniform distribution of electric fields around this sort of plane that we're sampling from, which is perpendicular to the direction of propagation of the wave. So when unpolarized light passes through a polarizing sheet, we are going to absorb half of the basically the intensity is going to drop by a half. We're going to absorb all of the horizontal components, which basically makes up half of the intensity of the waves. So regardless of the direction of polarization, whether it is vertical, whether it is horizontal of the sheet, or whether it is at some angle, for any situation when we have unpolarized light that is passing through a polarizing sheet, regardless of the direction of polarization, we are going to cause the intensity to drop by a half. The way that we write that is if the initial intensity of the wave is I subscript naught, and then after passing through this polarizing sheet, the intensity is I subscript 1, what we can say is I1 equals a half I naught. And remember, once the light has passed through the polarizing sheet, it is going to be polarized itself. So the intensity of the polarized light is going to be given to us by I, or I1, and it's going to be a half of what it was originally if the original light was unpolarized. But what happens then if we were to send that polarized light through another polarizing filter? What we need to do is, remember how we said before that we have 4 light rays that are orientated sort of at an angle. We've got a horizontal and a vertical component of the light. We're going to have we have a horizontal and vertical component of the electric field of the light. We're going to have to work out a similar sort of thing here. Now, the only light that is going to pass, or the only electric field component that is going to pass through the polarizing sheet, is the component that is parallel to the direction that the sheet is polarized in. For example, if we have light that is polarized in a direction that is, for example, an angle theta from the vertical axis, and we have a vertical polarizing sheet, only the vertical component of that vector that is at a polarizing direction of theta from the vertical axis, only the vertical component is going to get through the polarizing sheet. The horizontal component in this case is going to be absorbed. Now, we can make our little triangle here where the hypotenuse is the magnitude of the electric field vector E, and we're going to have a vertical component, EV or EY, and we're going to have a horizontal component, EZ or EX, or EH. And the way that we would write that is to work out what the vertical component is. It's going to be cos theta of the angle is going to be the adjacent side, which is going to be the horizontal component, EY, divided by the magnitude of that vector E. Therefore, EY is going to equal E cos theta. It is the component that is parallel to the direction of polarization. So this is what is actually going to be transmitted through the sheet. Now, remember that the intensity of an electromagnetic wave, it's proportional to the square of the electric field. And that is given to us by, for example, the equation I, the intensity, equals E RMS squared divided by C mu naught, or I equals E max squared divided by 2 mu naught C. So what this is saying then is intensity is related to the square of the electric field. Therefore, in our case that we're considering here, the intensity of the emerging wave is going to be proportional. We can say that the emerging ray after passing through a polarizing sheet is going to be proportional to I naught, the original intensity that it had before. And it's going to be equal to the electric field component that gets through divided by the electric field component that it started, the electric field that it started off with. Now remember, E, the electric field, is given to us by, E equals E max cos kx minus omega t. So we can say that the intensity then of our wave equals the initial intensity that it had, cos squared theta. So what does this mean in general? Well, this equation can only be used when light that reaches a polarizing filter is already polarized. Remember, if it's unpolarized, the intensity is going to be half of what it was originally. If it's already polarized though, we need to use this equation, I equals I naught cos squared theta. What happens when we change the value of theta? Well, we can see then that the intensity that passes through a polarizing sheet is going to be maximum when theta, which is the angle between the direction of polarization of the light that's coming in, is at 0 degrees or 180 degrees to the direction of polarization of the polarizing sheet. So the transmitted intensity then is going to be 0 or a minimum when the angle between the polarization direction of the light that's coming in is at 90 degrees or a right angle to the direction of polarization of our polarizing sheet. Now we need to remember that this isn't necessarily this angle theta, it is related to the relative angle between them. So for example, we can have a sheet that is polarized at 20 degrees and light that is polarized at 25 degrees from the horizontal, for example, coming in. The angle theta is only going to be 5 degrees between them. So we need to be careful about this angle because it's just the relative angle in between the light that's coming in and the polarizing sheet sort of orientation of polarization. It also applies to two polarizing materials or two polarizing sheets whose transmission axes are at angles of theta to each other. So if we have two sheets and they're at an angle of 10 degrees from each other, we can just apply 10 degrees. Similarly, if we have two polarizing sheets, for our sunglasses example before, if we turn them at 90 degrees to each other and we sub 90 degrees into our equation, cos squared is going to equal 0. That means the intensity passing through is going to be 0, and as it stands, I can't see anything through these glasses. So the maths and the physics make sense on this one. So like I just said before, if they're orientated, two polarizing sheets are angled at 0 degrees or 180 degrees to each other, everything's going to get through, all the light's going to get through and it's going to look normal. As we start changing the angle and approaching 90 degrees, then the intensity is going to drop and drop until we get a minimum at 90 degrees when no light gets through. So our intensity rules are as such. In really quick summary, if we have a polarizing sheet and the light that is incident on that polarizing sheet is unpolarized, then the intensity of the emerging rays are going to be half of what they were originally. If the light is already polarized as it hits that polarizing sheet, then the emerging intensity of the light is going to be given to us by the equation I equals I naught cos squared theta.